So good morning to everybody. I'm coming back to qualitative modeling using IPSIM, IPSIM tool, IPSIM software. And some years ago, I could not imagine that I could deliver a presentation of modeling, because at this time I hate modeling. I do not like at all mathematics, equation, and so on. And I think 2 years ago, I was exactly in the same situation that Dr. Chuk today, or last month in Italy. And now I can talk about modeling without complex. It's because you will see, as Jean-Noël said, as Chuk said, as Philippe said, the approach is quite easy. After that, you can do some very complex model if you want, with a very complex scientific question if you want. But if you have a clear question at the beginning, if you have a clear aim, you could design and build quite easy use model. So the first problematic for us was to improve our knowledge on the impacts of different factors on pest, and of course, in this case, on fruit flies on Chayotte. And the conceptual models using IPSIM aims to facilitate the development of agroecology, of course, to reduce the use of pesticides, and also to, and maybe I could say mostly, to exchange with all the stakeholders. So maybe it's the first time for you to hear that our aim, the main aim of our approach by modeling was to exchange with stakeholders. And remember, yesterday we talked about ACP and implementation, the agroecological transition case, and we said that it's difficult because we have to have a participatory approach, and we have to take into account all the approaches, all the roles of different actors in the frame. In our specific case, the aim was to design and build a model to study the effect of different factors, and we're coming back on that, that can impact on fruit fly on chouchou. Chouchou, it's okay? Yes. For me too. And the scientific question was to better understand what happens, about the effects of, for example, environment, pedoclimate, practices on the effects on fruit flies on Chayotte. And we had also specific objective or secondary objective, which are important, maybe to help to predict the damage in some areas, taking into account the change in practices, for example, to evaluate and to understand the impact, and also to help the farmers to understand how to manage their crop for the fruit flies management. So in this approach we use a conceptual model, a qualitative model, and one advantage of the model is that you don't need to have data sets, as Jean-Noël said before, to build and to design and to build such as a model. And we guess that conceptual models are also source for reasoning, helping even the scientists to improve the questioning in the research areas, in the research fields, and it's a good tool also for, as you will see, for discussion, for animation, for exchanging and sharing with different stakeholders, and mainly with farmers. So this software called IPSIM for Engineering Profile Simulator was developed quite recently. It's only 5 years ago by Marie-Hélène Robin and by Jean-Noël Roberto, that you can see here. And IPSIM is very easy software to use. It's generic and it's easy to use. And you can integrate 3 kinds of factors in order to explain the effect and the impacts of these factors on fruit flies, environment, practices, and pedoclimate. Here are the main steps to build and to evaluate a conceptual model with IPSIM. First one is to design the model, then to build it, then to gather and to enter the data from the fields in the model in order to compare with the the simulated data, and then, if it's necessary, to improve the precision of the model. So, as Jean-Noël said, IPSIM use what we can call a platform called DEXI. So I don't know at all what is there in DEXI. I don't want to know, but I know that all the equations, all the mathematics, all the numbers, the possibilities, and the combination and so on are inside of this platform, but never when you use the IPSIM model. So it's why it's quite easy to use, but it's quite complicated inside. For the conception of the model, we, as you have seen, you have on the diagram here, you take into account environment, pedoclimate, practices, and so on, to evaluate the effects on the bioregressors. And with that, you can answer to the previous initial questions, such as support for growers, but also evaluate and understand the impact, and predict maybe the damage of the flies. For the construction, you have to give some attributes, base attributes and aggregate attributes to implement inside the model, as you will see this afternoon, for example, in this software, saying just, for example, with simple scales, it's favorable for flies, for example, or unfavorable, or something very simple like that, with very simple scales. Then you have to take the data sets that you get in the field, and to enter in the software, just to go to the comparison between the simulated results and the observed results. And you can easily compare the results, observations, and simulations by simple statistical tests based on the confusion matrix, with a small test of kappa, to say if it's the model is of good quality or not. After that, you can, if necessary, improve it by looking what kind of dispersion, for example, of the data you have, or with a mathematical algorithm. There is a unit near the unit of Jean-Noël in Toulouse working on that, and they can improve only by mathematical algorithm the quality of the model. So now, if we apply that, you have seen it's very easy. We have applied that to the case of Chayotte. So the first thing is to design, to mind map, you see the question and the different attributes. So as you can see, you have the climate, you have the practices, and you have the environment, and that is the conception, the design of a model. And it took 10 minutes to do that. Of course, it's difficult to do that for us, because we have not to be wrong. If we are wrong here, the model will not be working. But it's quite easy to do that. And if we are able, by expertise, by literature references, not by data sets, so it's quite easy to do that. And I'm sure that this afternoon, for example, for your working groups, you will be able, maybe in an hour, to design such a concept, such a model. After that, we have translate that in the software. So it's exactly the same thing than here. You have exactly the same attributes. Okay, base attributes, aggregate attributes, and then, as Dr. Schupp showed this morning, it's a lot of combination taken into account by the software. And you have also, for each situation, to give a scale: good, not good, medium, and so on. That you have to share with people involved in Chayotte or involved in modeling, but mostly with all the stockholders. We talked about that yesterday in a participatory approach. We made a lot of we organized a lot of meetings with farmers, with trainers, with extenders, with policymakers, and so on, to exchange about this model and to see if they agree with it. And once we agree all on this model, we can, after that, implement it to compare if it's good or not. So, for example, you can see we gave some weight to the different attributes, and for example, we saw that the three main factors: environment, climate, and practices, had quite the same weight for the impact on the fruit flies. After that, we have a gaffer and translate all the data. One thing interesting is that you don't need always quantitative data. You can have quantitative data, of course, but you have to translate them in qualitative data, so it's quite easy. And you can transform also a criteria. For example, I don't know the number of fruit infested by fruit flies. You can also use, for example, a number of fruit flies, population of fruit flies, the damage of fruit flies. So a lot of criteria. You can use them, quantitative or qualitative, and you have to transform them just to be in line with that model requires. So that is, for example, a data observed. As you can see, it's not so complicated. It's in French, but it's just to show you that you have not so much variables. Then you have to enter that in the software and to compare after if the simulated prediction is good quality. As you can see here, you have for each situation a result given. Here it's in French, it means a low damage, for example. And after, when you take all the situation, the statistical test can compare all the situation observed and simulated, such as it's described on this figure. And with the matrix, we can have a result concerning the quality of prediction of the model. In this case, it's quite good with the scale of kappa, and so it means that the prediction of the model is good, and we can use it after for our aims: prediction, understanding, and also support to farmers and to decision makers. And you can also, after, improve it. So in this model, we saw, for example, that we have some over dispersion, and it's quite easy to implement by an iterative approach. Implement again in the model, and you have also a second step to improve the kappa indicator with a mathematical algorithm. So now, just to show you an example of how we use this model now in Réunion Island, and you will see it's quite different than the idea we could have on the use of modeling. We can show and discuss with farmers like that. Okay, I don't care of my crop, and a situation like that, as you can see, the model will say, okay, you have you will get a very high damage of fruit flies. The farmers can say, okay, I have a lot of damage in my crop. Okay, I can use pesticides to manage or to fight the fruit flies, and the model gives again an answer very high damage. So he say, okay, I stop to use the pesticide because they are not effective, and as you see, remember yesterday I talked about traps and CNAs and so on. So I can use the traps for the male annihilation technique, and still the model says yes, but it doesn't work. The damages are very high. So he say, okay, traps are not effective alone. I am going to try sanitation using augmentorium, for example, and here the damage decrease. But they are still moderate, they are not low. So he says now my practices are now effective, and my neighbor use also augmentorium. And as you can see, the damage decreased and became low. So it's very easy to change only one variable, for example, in a meeting, or even in the crop with a computer, with a farmer, to say, oh, look, if you use pesticide, that is ineffective, or and so on. So for the use of this kind of model, and it's why I was investigating in this modeling approach. Of course, it's a prediction of the impact of different factors on the pest. Of course, it's to support, for example, the decision makers to develop agroecological and new cultivation of chouchou in new areas. Of course, it's to support the development of new tools of agroecological crop protection, such as, for example, augmentorium. But it's also, and maybe mostly for me, a tool for example, professional training. Such as we use now in a professional training with a diploma. I talked about that yesterday. But we can use also that in a MOOC, in a massive online courses. And it's also a support and a space to discuss with different stakeholders. Of course, growers. And they can integrate also their empirical knowledge that they bring at the beginning of a process. It's the same thing for researchers. This tool can bring new questions of research to study. And of course, it's also important for decision makers, because with this kind of tool, they're very easy. They can understand what they have to promote or to combat. So we have built very quickly in 1 year a very good quality model on Chayotte. Chayotte was quite a simple situation. We are just finishing another one on zucchini. And we are going to try to create a model, IPSIM model on mango, and it will be more complicated. because we will integrate all the pests. We will also integrate, as we can, the beneficials. So it will be the first time we'll have so many insects, so many bioaggressors and beneficials integrated in this kind of models. Okay, and they show some paintings, and I like paintings, so I show also paintings with a very famous painting of Claude Monet, and a copy made by a Vietnamese artist very nice in Hanoi. Thank you very much.